In section 1.5, we're looking at properties of functions. The first property we're going to look at is determining if a function is even or odd. So for an even function, if we plug in the opposite of x into f of x, we will get the original back. All right, so if we sub in the opposite of x in for x, then you get the original equation. And that would make it an even function. So if we look at this function g of x, where g of x is equal to negative 3x squared minus 5. If we plug in the opposite of x, so we have negative 3 times the opposite of x squared minus 5. The opposite of x squared is opposite of x times the opposite of x. Those would cancel out. We're going to end up with, still have negative 3. This becomes x squared, and then we still have minus 5. We get the original equation back. Also, one other way we can determine is that we will have symmetry to the y-axis. Now for an odd function, if we plug in the opposite of x into f of x, we get the opposite of the original. So if we sub the opposite of x in for x, then you get the opposite of the original equation. So if we look at h of x, here we have h of x is equal to negative 3x to the fifth plus 5x. So if we plug in the opposite of x, here we have 3 times the opposite of x to the fifth power plus 5 times the opposite of x. Now, anything raised to an odd exponent, we have a negative number, the opposite here, so then this would remain negative, or the opposite, so that would carry to the outside. So we have negative 3 x to the fifth, and here we have basically a negative 1 as our coefficient, negative 1 times 5, so minus 5x. So this is, if we factor out a negative 1 times 3x to the fifth plus 5x, that would be the opposite of our original equation. So that would be equal to the opposite of h of x. Also, when we look at an odd function, we have symmetry to the origin. Here we're going to use a graph to determine whether this function is increasing, decreasing, or has constants, as well as finding local mins and maxes. Now when we're doing this, one thing we want to look at is when we write these intervals, we will write them in terms of our x values, and we're working from left to right. So for A, the question asks us to list the interval of which, or intervals, of which f is increasing. For B, we're listing the interval or intervals of which f is decreasing. For C, list the interval or intervals of which f is constant. D, at what value or values of x does f have a local maximum? E, what are the local maxima? Now we're naming that as a point. F, at what value or values of x does f have a local minimum? And for G, what are the local maxima? Again, writing that as a point. So now pause the video and use this graph to go through and answer those questions, and we will discuss it as you're finished. So for A, when we are listing the intervals of which f is increasing, remember we're looking here at the graph, and as this is going up from left to right, this is increasing, and when we name the interval, we're naming it by those x values. So from negative 6 to negative 3, this graph is increasing. We do not include That's why we use parentheses to show -6 and -3. It's increasing in between there. It's also increasing from 0 to 3, and then it's also increasing from 6 to 8. Where the intervals f is decreasing, it's decreasing from -3 to 0, also decreasing from 4 to 6. It is constant from 3 to 4. That is a straight line where that graph stays the same as far as our y value goes. It is constant from 3 to 4. Now the value has a local max at -3. Now to have a local max, that means on one side it is increasing, on the other side it is decreasing. So that would be a local max. And then here where we're writing the local maxima, now we write that as an ordered pair. We're talking about the ordered pair -3, 4. So f of -3 is equal to 4. That is our local maxima. The minimums are at 0 and at 6. Again, to be a minimum, we're saying that on one side it is decreasing, the other side it is increasing, so that is a minimum value. It has to be increasing and decreasing on either side to be a max or a min. And again, for the local maxima, we write this as an ordered pair. So f of 0 equals -2 would be this point, and f of 6 equals -1 would be this point. When we're discussing the average rate of change, the definition says if a and b, where a is not equal to b, are in the domain of a function y equals f of x, then we find the average rate of change by taking our change in y over our change in x. So we would find f of b minus f of a all over b minus a. Now really what we're saying here is that we have our point where we're going to find our change in y over our change in x. We're finding the slope. We're just going to find 2 points that are on that graph, and we're finding the slope of the line that's in between those 2 points. And that would be our average rate of change. So if we have h of x equal to x squared minus 2x plus 3, let's find the average rate of change from -1 to 1. Let's also find the average rate of change from 0 to 2, and then find the average rate of change from 2 to 5. Now remember, these are our x values. We need to find our y values, or what the function is, h of x, when we plug these values in. So you need to first find your points, then we would find change in y over change in x. So when we plug in -1 for x, we find that h of -1 is equal to 6, and when we plug 1 in for x, we find that h of 1 is equal to 2. So that gives us our first 2 points, and then we can find the average rate of change in between those 2 points. From 0 to 2, h of 0 equals 3, and h of 2 equals 3. And for our values from 2 to 5, h of 2 equals 3, and h of 5 equals 18. So now we can find the average rate of change between these points. So now we take change in y over change in x, so we have 2 minus 6 over 1 minus -1 gives us an average rate of change of -2. And from 0 to 2 we have 3 minus 3 over 2 minus 0 gives us an average rate of change of 0. And from 2 to 5 we have 18 minus 3 over 5 minus 2. That's our change in y over change in x, gives us an average rate of change of 5.